First thing I'm going to have you do, go to your calculator on here. So go take it out, and you'll notice that under your mode button, you've now are going to be moving over into the third mode option. You've lived under function mode for the most of your school career. We moved into parametric for a little bit and we were plotting, but we were still plotting x comma y. It's just they were controlled by the time parameter, but you were still on the xy graphing system. The polar system's different. It doesn't get plotted on an xy. So that's called a rectangular grid because you go over x, up y, and if you did full cycle, you make a rectangle. So that's called rectangular system. In the polar system, that's not how things work, but we'll get to that in a minute. Just hit your y equals button so now you can see what it says. It says r equals. It doesn't say y equals or x equals or y of t, x of t. It's r. So, and that actually stands for a radius. So you're going to be working with a lot of radii. We're not going to graph anything yet, and we'll be on here a lot tomorrow. We'll kind of be looking at what these make. But even if I were, let me enter a fake one so you can see. If you were just to do 3 plus cosine theta, and notice now when you hit the xt, the button that's always been your go-to for x, you actually get that third option where it says xt theta. And if you were to graph that, I don't know if my window's set right, so my odds are it's probably, I don't want to go check my window though, let's just see if it's okay. All right, so make kind of a circle-y thing, right? No big deal, not fancy, but they do get kind of fancy. So what I want you to do in your notes, we're just going to go talk about in basic, how do you plot points? How would I be able to graph by hand in polar? And just the vocabulary of it. So when we're in rectangular coordinates, you already know that every location you give has an x and a y value. So you go over x, up, y, and when you go over up, it's kind of like part of a rectangle, and it's a rectangular system on a square-based grid. So in polar, though, you don't give x and y. You can still talk about x and y, and you can still get x and y, but that's not how you go locate things. What you do is you give a distance, and we call that r. So you get told how far to walk, basically. And that actually tells you also which direction to walk. So it's kind of going to be like you're walking, but not right and up, like in this square motion. You're going to be walking a certain distance along a certain angle. So we have lots of r's and thetas that happen in polar. And the first thing you need is a polar axis. So generally, your polar axis, it says, is usually the positive x-axis. For us, it always will be. So you're going to have what's called a polar axis, and you're going to be walking away from the pole. So really, if you were to kind of think of this xy coordinate system, this polar axis is really just facing 0 degrees and along the x-axis. And the pole is really the what? Origin, really. So to specify a point, you just have to tell somebody, well, how far do I walk away from the pole? And then you also tell them what angle you walk. So you actually don't have x, y, you have r's and thetas that go in your coordinates. So it goes r theta, which is going to kind of bother you. Every point is given by a radius and a theta, because you're used to getting x first and then y, right? And x comes first. But in polar, you actually do theta first, so you actually rotate and then walk. So your independent variables in the opposite slot. So that is a little awkward to work with. You're going to find yourself by accident writing them in reverse, because you're going to go, oh, it's pi over 3 and I walk out 5. So you're going to want to write pi thirds comma 5. But it's the reverse. So it's kind of like a sneeze if you were to r theta. That's kind of how it goes. If you were to sneeze like theta r, it doesn't sound right. So when you're about to write it, just r theta, like you're like a sneeze or something. I don't know. I even found myself on one of the keys I was making yesterday for this unit. I wrote one of them backwards, and I've been doing it for a while. I still sometimes, because you're so locked into that, okay, x first, then y. On here, it's theta first, then r, so you feel like it's awkward. You'll get used to it. And it's not a huge deal, to be honest. The stuff we do today with the, trying to extend my page here. There we go. The pre-calc part of it won't be on your AP exam, but it's necessary for a deeper understanding of all the stuff you're going to be doing. So again, this would have been specified as r theta. So you point, you're actually looking out, you rotate theta. It's like you're facing this way and you walk out however far r is, and that's your point. Seems fairly easy, and it kind of is, but there's another thing that's weird. So this is what a polar system looks like. It still looks x and y-ish, but it's not. Usually they go by pi sixths, sometimes by pi twelfths, but this is a standard polar grid. A standard rectangular grid goes 10 by 10 in both directions. So it also is kind of like if you think of the North Pole, and if you're like looking down on it, it's kind of like those latitudinal lines that you would see. So anyway, let's go put a point P on here and we'll talk about it up here first. If I were to go and say I would like you to rotate 2 pi thirds, and I give you the angle first. All right, so let's talk about if I told you to go 2 pi over 3, right? So you're actually facing this direction, you rotate to 2 pi over 3 and you're facing it along that ray. And then if I were to say, I want your radius to be 4, well, it's really easy. You just start here, you rotate, and then you go 1, 2, 3, 4 radial units out, and this would be considered the point P. I want to be very careful though, because in the rectangular system, there's only one way to get to one location. If you want to go to 5, -3, you have to say 5, -3. That's it. There's no other way to get there, right? In this system, there's 4 ways correctly to get to every point. Why do you think that is? You can anticipate the angle. I could easily change that angle, right? And still end up on this ray emanating from the pole right here. Instead of using 2 pi thirds, what could I do? What do you think? There's a whole nother way to get over there. How? A negative something. Yeah, so I could have done negative, right, and then walked out. Also, we can mess with the r, because a negative r means you walk backwards while facing that direction. So it gets a little confusing. So we're going to go to this next one and put point P on my grid. We're going to write it all 4 correct ways. There's the standard way, but there's 4 proper ways and correct ways you can get there. So let's go make P so that it looks like it's a little bit more on that 1, 2, 3, 4th radial line. What theta does that look like? What's the most one that comes to your mind first? 5 pi over 4. So we'll write the easiest notation first. First of all, let's point out, all right, and we're going to rotate from the pole. That looks like pi over 4, so let's go put a pi over 4 in there. So the most standard and easiest way to write this point would be to write it as, what comes first? You rotate first, but r theta. So you put the r down first. That point would be 4, comma, pi fourths, but there's actually 3 other correct notations for it. And the negative part screws people up, because I'll wait till I get to the next page. I'll show you. So let's go write that another way. If I still want to walk 4 units forward along that ray at pi fourths, I could rotate backwards. That's the easiest one to get next. So how many degrees would I have to rotate this way and then walk away from the pole? 7 pi over 4. Yep. So I could call that 7 pi fourths and still walk forward 4. That's totally legal and that's appropriate. However, if, I'm going to erase this red one, if I were to, and we're going slow today because it actually, the more you understand this, the easier the calculus will be. I could actually rotate all the way to here, to this ray, but not walk forward along it. Walk backward. So you always have to face in the direction, and if you use a positive, you walk that way, which it seems weird because you're going in a negative direction, but that's XY system. A positive R just means you're walking along your ray. A negative R means you're walking backwards along your ray. So I could call that angle, I could rotate to here. What's this one? What's that angle over there? That's what 5 pi over 4, but instead of walking 4 forward and going out to here, I could walk 4 backwards and get to P. So you call it -4. That's all the same stuff. It's weird because we've got now 4 ways to go to one location instead of our usual. That's a bad 5 pi over 4, isn't it? Let's make that nicer. So see if you can think of the 4th way. There's always two with a positive R, two with a negative R, two with positive angles, and two with negative angles. Okay, so did I do one back? Oh, did I forget the negative? Sorry. All right, so go to the fourth one and see if you can walk backwards but turn a different way. It's not that difficult, right? I could go backwards or I could go clockwise this time. How far would I have to go? What? Go ahead. Yep, 3 pi, negative 3 pi over 4, because I'd go backwards. So let's go ahead and write that, negative 3 pi fourths. But then I wouldn't walk forward along that way. I'd have to back up. So it would be with a negative 4. So it's awkward. It's not difficult. It's just not what you're used to. And you might say, well, why do we need, whoever came up with polar and what's it good for? It's really good at dealing with curvature and things that aren't functions. It makes their representation so much prettier. For things that are already function and nice y equals and a single x, those always look better in rectangular. But curvy things, if you don't put them in polar, they have to be strung together with a bunch of piecewise things, and it gets to be a huge disaster. So polar kind of accommodates things that aren't functions and things that curve very well. All right, so let's go plot a few on here. Let's go just take, and this is going by pi 12ths, but it doesn't really matter. Let's go put a point right there, call it A. I want to deal with that one. I actually want to deal with B right here, and then maybe that's probably good enough for you guys. If I was actually teaching pre-calc, we'd sit and plot points now for quite a while, but I think 2 ought to do it for you. So let's go on here and let's talk about A. Let's just do it 2 ways. So the most standard in what you usually think of for that, A, would be located at angle first. So the most obvious turn would be to do the positive one, head out and go 5 pi sixths from your polar axis. So you turn this way and walk that way. So that would be a 5 pi over 6. And then can somebody count those? How many radials is that? Is it 7? I think I did a 10 grid. So you'd have to count them. You'd have 1, 2, 3, 4, 5, 6, 7. Yep, 7. So you have to count those concentric circles. So that's one way. Name it one way with a negative R for me right below it. Basically what that means is face on the opposite ray, but walk backwards. So let's get one more name for A, and then we'll move along. You got one for me? How else could you name that, Jen? Give me a good one. I can go negative, how many degrees? But I would just go this way, like right to here. I'm going to do it in green so you can see it. I'd turn this way. How many degrees would that be? Help me out. You guys never talk when I have my headset on. They can't hear you. It's right by my mouth. Thank you. Yeah, you could turn negative pi over 6, but you can't walk in that direction. You have to walk backwards. So that's another way. But there's 4 correct ways. Normally you gravitate towards the first one because that's kind of how you're used to turning. B right here. Let's go take a look at that one. This is the kind when you're on those cornerstones with the zeros, that's where people get the most screwed up. And here's why. When I turn the positive direction and go to this ray, how far did I turn on that one? 3 pi halves. So if I'm going to use an angle of 3 pi halves, what a lot of people do, they see this as being at negative 8, but that's in the XY coordinate system. You are still going to walk forward along this emanating ray. So that's actually a positive 8. If you're going to walk backwards, right, then what would your angle be? Pi halves walk backwards. So it'd be pi halves and a negative 8, but it's written in reverse. Do you see how it kind of messes with your head? And it's not because it's more difficult than the XY coordinate system. It's just you've been doing that forever. It's kind of like you throw with your right hand for 20 years and then you try practicing with your left. It's awkward. but I'd argue that they're of equal difficulty. Anyway, relationships between polar and rectangular. So now we're going to convert back and forth between the two for a little bit. So we have on that previous page, I'm going to have you go look back here. What if I wanted to take, let's go down here. I was going to say I thought I put something like that on here. Go down on the bottom of this page. I'm going to erase this. I'm going to go back and draw this. And we said it was pi fourths, and we walked out 4. You can easily convert from polar to rectangular if all you know is SOHCAHTOA. Because if I pull out this, yes, it's 4 radial units, but actually along the x-axis, it's about 2 point something. Because this still represents 1, 2, 3, 4, right? But this is just between 2 and 3. And I can figure that out. All I need to do is know my SOHCAHTOA. So if you go let's go draw an arrow up here so you know I'm referencing that one. So if you go on here and you call this pi over 4 as your angle, I'm going to write it nicer. Boom, boom, pi fourths. Label this x, label this y, drop it down, and this is still r, which in this problem was 4. You can figure x and y out. Just use your trig functions. So if you were to say, wanting to find x, this is a 4 over here, it's tipped sideways. What trig function deals with this length and that length that you're used to from 9th grade geometry? Cosine. Yeah, so if you say the cosine of your angle has to equal adjacent over hypotenuse, then the x distance actually in the rectangular system is 4 cosine pi over 4. That's what x is. So it'd be 4 times root 2. It'd be 2 root 2, correct? So that's actually a walk of 2 root 2 along here if you're considering this the x-axis, not the pole. All right? Likewise, go do the y one over here. You know what that's going to be. It's going to be 4 what? 4 sine pi fourths, 2 root 2 again. I knew they were going to be the same because of a 45-degree angle, but let's replace these with their variables. This is r, this is cosine theta. So you can always find the x coordinate by just doing r cosine theta, and it's easy. How do you think you always find the y coordinate? R sine theta. That's the conversion from polar to rectangular. So what we're going to do is write out some more relationships and then we'll get it solidified. So let's go make a fake angle. Let's call it theta, an unknown x, an unknown y, and an r. These are all the things you're going to be working with. Theta, r are our polar stuff. X, y is what you're used to, but you can ebb and flow between the two pretty easily. So we already said that x is r cosine theta from the previous page because you do cosine theta is x over r and just multiply by r. We know y is r sine theta, so that's your conversion if you want to get out of polar. Now, how are x, y, and r all related? All the lengths are related how? By the Pythagorean theorem. So we also know that x squared plus y squared equals r squared, or even better, r is equal to the square root of x squared plus y squared. That'll help you get out of rectangular and into polar. So if you know the x, y's, you can find r easily, Pythagorean theorem. The other thing you would need if you were trying to get out of the rectangular is, well, how do you get theta? Can someone anticipate, if you know x and y, how do I get theta? Tan, yeah, that's another trig function. So if I know that tangent of theta relates y to x in this manner, then I can get theta by just doing what? Tan inverse, yeah. So theta is always going to be arctan or tan inverse. And if this were pre-calc, you'd write it as tan inverse, so I will. We use arctan in here because this looks exponent-y, but we're good. So here's all your relationships, and on the next page, I've got them all up there. Those are kind of your go-tos, but on the AP exam, do you think you have to do that? Convert between the two and all that? This is considered pre-calc. What you have to do on the AP exam is take a polar curve, kind of know what it looks like, find derivatives, find slopes of tangent lines, find areas of petals, and all that good stuff. But this is a precursor. So we're just going to practice today. Let's go take a look. If I'm going from polar to rectangular, rectangular, that means I'm going from our theta to xy, and it's just an easy conversion. X is equal to what? According to our models, x will be 3 cosine theta. So there's lots of trig in here, lots and lots of trig actually in polar. You can see why. The trig issues will really hurt you in your polar stuff. What is the cosine of negative pi over 6? It's the same as the cosine of pi over 6, which is which one? Root 3 over 2. Yeah, so that would be root 3 over 2. So 3 root 3 over 2. My y would be 3 cosine negative pi over, sine negative pi over 6, which isn't the same as sine pi sixths, right? What is it? Negative, yeah, so that would be 3 times negative a half, or negative 3 over 2. So that point, watch, that's location is, go put a dot where you think that is, and let's go see if it gets confirmed rectangularly. And again, be careful with what negatives mean when you're dealing with angles and those radial units. You should rotate negative pi sixths and then walk along that ray forward. So you actually do end up in a quadrant that has negatives, but that's only if it's xy. So you should take your pole, rotate pi 6 this way, and walk 1, 2, 3 radial units out. That's the location of that point. When you convert it to xy coordinates, I now know that I would go this and then this. That's what I found. That's 3 root 3, and that's negative 3 halves. So you can kind of see how that goes. I don't think we need to do another because that's easy. If you have degrees, which you might, then just work with it. All right? Actually, let's do this rectangular to polar right here. Now I'm on xy, and I want to go r theta. So how do I do that? R is easy. How do you get it? Square root of x squared plus y squared. It's the hypotenuse of the right triangle. So my r is just going to equal the square root of 4 plus 36, square root 40. Go ahead and simplify it if you want. R is always easy because they have to give you both x and y, and you just use the Pythagorean theorem. Now this is where you got to be really, really careful because you really have to understand what your calculator is doing and adjust, because your calculator is only as smart as its operator. So if I want to get theta, what did I tell you you do? So everybody watch, even if you kind of tuned out, you're like, this is easy. It should be. This is normally in a pre-calculus class, but this is what's going to trip you up. Tan inverse, right? Y over x, so it'd be 6 over negative 2, which is negative 3. You're going to go to your calculator, and it's going to give you an answer that is not our answer, and we have to understand why it's doing that and how we can adjust it. All right, so go do tan inverse negative 3, and what does your calculator tell you it is? Go ahead and tell me. I'm going to go off to the side and call it alpha because it's actually not our angle. What does it tell you it is? I don't know because it's not on the unit circle. I have no clue. But I know it's going to give you a negative 1.249. Can someone back that? Negative 1.249, right? Well, that's telling me, watch how you've got to kind of use some common sense. I'm supposed to be 2 units to the right, so 2 radial units to the right, 1, 2, 3, 4, 5, 6 up, and complete the rectangle. So actually watch, that's why it's called rectangular. You go 3 that way, 1, 2, 3, 4, 5, 6, is that right? 1, 4, 5, 6 up, and then you complete the rectangle. My point is up here rectangularly. I'm going to erase the rest of it. It's hard to map out because you've got it's up there, correct? But this angle they're giving me is down here. You might say, well, how far down is it? Right here, let's go this way. If you were to go all the way to this one, how far backwards did you go? Negative what? Pi over 2, which is about 3 over 2, which is about negative 1.5 radians. So negative 1.2 radians is kind of like right in here. Do you see how it's giving me this one? Here's why. There's always 2 places on the unit circle where you have the same sign and the same cosine. Your calculator can only give you one of them, right? Your calculator can't give you 2 answers at once. Does that make sense? So what it does is it gives you one of them. And for tangent, it always gives you one in its most logical domain. And tangent's domain runs from here to here. So it always will give you, if it's positive, it'll give you this one. If it's negative, it'll give you that one. That's what your calculator's been programmed to do. So you have to monitor and adjust. How do you go from knowing that you need to go negative 1.29 radians this way? So actually, let's go put that on there. It'd be about, it's actually directly about to here. Negative 1.29, that's what you know. How do you figure out what this one is? And it's from pre-calculus. It's some sort of plus or minus. And when I used to teach this in advanced math, they would struggle and try to do it with formulas like, do I add pi? Do I subtract pi? Do I subtract from pi? Do I subtract from 2 pi? Don't do it that way. It's all about the gap with the x-axis. What is this gap right here? Positive gap, what is it? 1.29, correct? So what's this gap right here? 1.29. So I do pi minus 1.29. Do you see what I mean? It's all about, if it was down here, I do pi plus it. See what I mean? So it's all about the gap it makes. And do you have to do this all the time? No. It's actually only for tangent generally, or cotangent, which we don't use. You could use cotangent actually, because you could do cotan inverse negative 1/3, but what would be the point? That would be silly Sally. All right. Anyway, so I need to do pi minus the gap with the x-axis. So you can kind of remember that. It's pi minus whatever the gap is. Can somebody give me what that is? Because I don't know. What is it? 1 point. Help me out, Sully. 89. Okay, so that's your theta. Now try this. Do tangent 1.89 just to test her out. Tangent 1.89, what does it tell you? Yeah, it'll be close. We did some rounding, 2.999. So you can kind of test it out if you're in the right spot. All right, so when I'm converting, again, from polar to rectangular, I just do my x is r cosine theta, my y is r sine theta, and it's easy peasy. So I don't think we need to practice that. Again, I took this off of a pre-calc site, so that's a no-brainer, right? We're good with that. Let's try going backwards on a couple and have a discussion. This one, R is a piece of cake. What is it? R is always easy to get. Square root of 25 plus 144, root 169, 13. In a sense, I'm insulting your intelligence, but in a sense, the details are actually what's most important. So yeah, that was easy. Then to get theta, right? The tangent is y over x. You need to tan inverse it and then decide if that's your answer or not. And the answer is, if you're in the first quadrant, your calculator will give you that angle correctly. So go ahead and do tan inverse 12/5. Some people are under the misconception that the trig functions can't go past 1 and -1. Which ones can't? Which ones can't exceed? Sine and cosine are the only ones blocked in by 1 and -1. Tangent, actually, you could have this be 1,000,000,000/7, and you would remember, because it goes to infinity. Does that make sense? So you have an infinite range for tangent. What's the answer? I don't know. What is it? Theta is? Help me out. 1.176, and just so you understand graphically what that means, it means for you to plot the point 5, 12, you would need to rotate from the pole 1.17 radians and walk out 13. That's what that's telling you. All right, next one. You should be able to do that with common sense and no math. Think of the point 0, -2 on the rectangular coordinate system, which is right here. But for polar, what angle will you rotate? How are you going to get there? Right? I shouldn't really need to do anything on my calculator. How am I going to rotate? 3 pi halves. Or -pi/2 is legal also, but we usually will, theta equals 3 pi/2. You don't have to list all of them. The radius is obvious. What is it? 2. I mean, anything on these polar edges. There it is. Now this one we've got to kind of be careful again how we think about it and how we use our calculator. R is a no-brainer. It's just the square root of 25 plus 25, square root of 50. You can do that in your head, etc. But be careful when you do the tan inverse. You almost should think about it, right? Where is negative 5 located? Which quadrant? Yeah, negative 5 is going to be in the third quadrant. So it's going to be over here somewhere, right? I know I need to walk 5 or 2, but what angle is this rotation? You should know that because it's on the equal to line. What one is that? That's 5 pi over 4, correct? Now if you tan inverse 1, watch what it gives you. It won't give you 5 pi over 4. It'll give you the angle over on the right that has the same tangent. So guess what it gives you? Pi fourths. So you have to be a little tad bit smarter than your calculator and think outside the box, because if you go tan inverse 1, your calculator for tangent locks you over here. It just can't give you both. So, all right. So theta on this one would be 5 pi over 4. So easy stuff, but details. All right. So we can also convert equations, and then we're going to talk about who's better and when. So all of these, you should know what they look like rectangularly. So let's go graph these in our old-fashioned coordinate system. Only one of them is better in polar. Can you anticipate which one's going to be better in polar? The third one, right? Because it's got curvature, it's not a function, y is squared. Whenever y is to an even power in rectangular, you ain't got a function, right? Have you been taught that before? Yes? All right, so y equals 2x plus 1 looks like that. Oops, I meant to hit 1, not 0, but pretend I did. All right, y equals 4 looks like this, and this is a circle with radius 4. All right, those are all their rectangular. We're going to go look at what they would be in polar, and then we'll go graph them in polar so you can see it jive on your calculator. All right, so when I am going out of rectangular into polar, I need to go to r's and thetas, right? And basically what that means is I kind of just need to go to r's, because instead of y equals, when you press your polar button, what does it say? R equals. So you need r as a function of theta. So we're going to replace y with its polar version. What's that? R sine. Yep. So we're going to call this R sine. And again, nothing's difficult. It's just going to be very awkward. R cosine theta plus 1. I want to solve it for R because, again, just like in Algebra 1, you got to solve it for Y. I need to solve it for R, my dependent variable. So if I'm solving this for R, what's my attack? And it looks weird, but you've solved stuff like, if you had this, like, x times 8 equals 2 times x plus 1, and you had to solve that for x, what would you do? Bring it all on one side. Exactly. So I'm going to do r sine theta minus 2r cosine theta equals 1. That's what I'm going to do first. Then I'm going to factor an r out. It's kind of like implicit when you're trying to get that thing by itself. I'm going to factor it out, right? And now I'll just divide by what's in the way. So my function r in terms of theta in polar mode would be 1 over sine theta minus 2 cosine theta. Just trust me. I don't want to go back to my graphing calculator. If you entered that in polar mode and hit graph, it's going to make that line. Did you already do it? It makes that line. So watch what happens. Again, this is way worse than this, and that's because this is already a nice linear function. It's pretty, so it's good. All right, let's go do another one. Y equals 4. I'm going to replace this one with its polar equivalent, r sine theta. Right, Aaron? And I'm trying to just figure out y. So what am I going to do to both sides? Go ahead, Benny boy. What am I going to do? I'm picking on the Sleepy Sallies. Yes, no. While you were sleeping, I said, our goal is to solve for r in terms of theta, so we just need to isolate r. It's a very easy question, right? Divide by sine theta. Yeah, so my r is 4 over sine theta or 4 cosecant theta. All horizontal lines actually in polar are cosecant functions. What do you think, anticipate, what do you think all vertical lines are in polar? They're secant functions. Can you graph vertical lines in your function mode? Can you graph them now in polar mode? See what I mean? So it tackles that issue too. Anything not a function like a vertical line doesn't matter in polar. See what I mean? So it's kind of nice. This one you could either outsmart it or you could do monkey see, monkey do. So give me one way I could figure this one out in polar. What could I do? Just see this. Oh, see, you're doing not monkey see, monkey do. You're outsmarting it. He's seen this whole chunk in polar. What's x squared plus y squared? R squared. And I'm almost there right away. Now here's a good question. What's r then? It's actually plus or minus 4. If you go, now I do want you to go to your graphing calculator, go to polar mode, and just do r equals 4. Your graphing calculator will graph a circle with radius 4. How easy is that? If you hit negative 4, it does also. Guess what it just does? It goes backwards. And by the way, if you want to see it looking like a circle, do you remember what you hit so it makes it nice? Zoom, square. Yeah, and then you'll actually see the circle. But what a slick way. In polar, if you want to graph a circle with radius 5, you type r equals 5. That's it. You're done. How nice is that, right? In rectangular, how do you graph that? You could. But how did you have to tackle the circle and make, I don't know, you could do that. Yeah, you could think of it in vertex form, but then still you couldn't go get it on your calculator. You could graph it by hand. But do you remember you had to solve it for y, and then to tackle the non-function part, you ended up with a plus or minus, and you had to enter it as two separate y's. Right now, if you ever want to graph a circle with radius 7, go to polar mode and hit r equals 7. It's slick. All right, he did it outside the box. What most people will do, and if you looked in a textbook, they would say this is r cosine theta, that's squared. That's what x is. Y is, don't write this in your notes, r sine theta, but you can kind of see what's going to happen. You're going to have an r squared that you pull out, and what's cosine squared plus sine squared? 1. So you're going to get the same result. So I like that you said that. You're pretty cool. All right. So going the other way is much more difficult. Going from rectangular to polar, not so bad, because you just replace those. But this one's a little weird. I want you to write over here. You're going to use your trig ratios a lot of the time. And they're the trig ratios on this layout. So when you see cosines and sines and cosecants of theta, you're going to replace them with things that have x's and y's and r's in them. It makes it easier. So right here, I'm going to leave this r right there. And you might say, well, why don't you replace it with x squared plus y squared? I could, but I'm thinking ahead. Okay, what I'm hoping happens is it cancels out and I don't have to do that. It may or may not. I'm going to write cosine theta in terms of its ratio. What ratio gives you cosine? It'd help if I put the theta on there. What ratio gives you cosine? X over r. Unfortunately, the r's did not cancel, right? I end up with this. R squared is equal to 2x. That is a mix of the two, which never shall you leave. That makes no sense to anybody in math. So now I need to deal with the r squared. What will I do with it? What am I going to replace it with? X squared plus y squared. Now, this one actually has a good thought process for graphing tomorrow. Come on, move. X squared plus y squared equals 2x. That's not a function. How do I know that? Y squared. So I know I've got curvature. But here's the deal. If you solve it for y, it's correct, but it's not in the form, you'll recognize it. I know what this is because I've done enough of them. You don't know what it is, but after tomorrow when you graph a bunch, you're going to look at that and know exactly what it makes. You won't even have to go to your calculator. But if I were to, I'm going to morph this into something you recognize, and then we'll go graph it. So watch. If I do this, and I move that 2x over, by the way, if on your homework, you solve for y. I think that's what I have on the key, because that's technically what you do. You'd write y is equal to plus or minus the square root of 2x minus x squared, but that I don't know what it makes. So I'm going to get it in a little nicer form for you, because you guys are smart. All right, I'm going to go like that. How, can anyone anticipate what I'm going to do with those x's over there? That x squared minus 2x, an oldie but a goodie. It rhymes with deplete the where. Good job. Yeah. I couldn't think of anything funny that rhymed with it. Deplete the where. All right. So you are going to tack on something here to complete the square. What are you going to tack on? 1. You do not need to do this on your homework, by the way. I'm just taking this to another level. I'm going to write right here. On your homework, you can just solve that for y. Y is equal to plus or minus 2x minus x squared. But you don't know what that looks like. Okay? And it has to go in as 2 pieces on a calculator. So I'm going to do that. I'm going to leave the y squared here. If I added 1 to the left, I must also add 1 to the right. So that bumps that. So basically, I got the same stuff. For all you people who never understood complete the square, it's just adding the same stuff onto both sides. I've now created x minus 1 squared, and now you should go, oh, I know what that makes, because now it's in a standard form of a what? Circle that's been shifted where? 1 to the right and has a radius of 1. Yeah, so go take out your graphing calculator and in polar mode, graph 2 cosine theta. And you'll see that exact thing. You're going to see, I knew before I started because there's a pattern, but it's going to have a center here and it's going to go like that. It's got x-axis symmetry and a radius of 1, and it goes out to 2 on the polar axis for a reason that we'll deal with tomorrow. That's pretty easy, right? All right, so the next one up, letter B. How do I get out of theta? Well, here's what I do know. The tangent of theta has to equal the tangent of 3 pi over 4, right? Tan both sides. What's tangent 3 pi fourths? -1. Okay, so tangent of theta has to equal -1. How do I get out of tangent, out of my trig function, into x's and y's? Who am I going to replace tangent with? Y over x. All right, and this is going to make total sense to you in just a second, even though it's awkward right now. This is actually the line y equals -x. Well, think about it. It's like a horizontal or vertical line in the rectangular system. When it just says y equals 4 and there's no x's, x can be anything, right? When this says theta equals 3 pi fourths, what can r be? Anything. So this says no matter what your radius is, no matter where radial units you are on the 3 pi fourths radial line. Be it forwards, backwards, r1, 2, this is the polar version. Yes? They're not both negative in this quadrant. 3 pi over 4 is right here. I think you're thinking 5 pi over 4. One's positive, one's negative, right? I'm good. Tangent 3 pi fourths is -1. It'd be I'm good, right? Yes. And those are exactly the same thing, so it's kind of weird. Yeah. How? No. That's like at the vertical line. Yeah, I said, yeah, you can graph anything in polar, but no, you can't. You can graph just, it's kind of weird, the connections. In rectangular, you can graph the y equals, but not the x equals. In polar, you can graph the r equals, but not the theta equals. So that's similar. Good thinking. Now watch what happens with this one. Again, I would give you the x-r-y ratio for cosecant. It's the reciprocal of sines, right? And sines is y over r. So who am I dumping in for my ratio right here? R over what? Y. Right? Now, technically that's yr equals r. Or really, you know that y has to equal what if these are equal? Just common sense. What's y? This is a horizontal line at 1. Look at when we went that way up there with the cosecant the other way. We got a horizontal line. So I'm going to have you try 2 tricky ones and then kind of an easy deal. So if you're going to polar, what would your gut tell you to do on the top? What would your gut tell you to do if you had to get that to polar? You don't have that. Sorry, write it on the back of your packet. Sorry. I added them when I was making the key to the worksheet. I'm like, I better put 2 harder ones on the notes because the worksheet's got a couple of these. Anyway, so what would your gut tell you to do? If you need to go to polar, you need to somehow introduce r into your picture. R is x squared plus y squared. So what do you think you would need to do with this one to get her moving? Foil it. Yeah. So you're going to get it so you can actually see. You're going to have a y squared minus 4y plus 4 upon foiling that. By the way, this is a circle, right? With a center at 0, 2, and a radius of what? It's a circle, right? And a radius of what? Actually 2, right? Yep. Now watch what happens. These 4's go. And what can I replace this with? I'm going polar. So what am I going to replace this with? R squared minus 4 times, what am I going to replace this with? I got to get it out of there. Who's r sine theta? That's actually very important in here. That needs to equal 0. Again, what am I trying to solve for? You're so used to solve for y. In polar, we solve for r. So what am I going to do to solve this for r? I'd factor it out, and you get r times r minus 4 sine theta. R can't be 0 or you're just stuck, right? You have to walk somewhere or you're just turning. Well, so it has to be that R is equal to 4 sine theta. This, if you were to go graph it on your graphing calculator, makes this circle. This one's way nicer. All right, and last up. Now work the other way. So it's very awkward, but it's not difficult. I want to convert this sucker to rectangular, which means I want to get r out of there. So I want to somehow have x squared plus y squared is r squared. That ain't happening here. I want to maybe get r sine thetas, r cosine thetas, so they can swap out with x's and y's. Do you see where I'm going to go with this? I'm going to take this denominator, and guess what I'm going to do with it? What do you think I'm going to do with this whole chunk? Bring it over onto the left so I can see some r sines and r cosines and see some x and y sub going in. So that's going to be r times all of this. I'm going to separate it. So it'd be r times 3 sine theta minus r times 4 cosine theta if I were to distribute it out. Well, what is r sine theta? Y. This is 3y. Minus r cosine theta is x, 4x equals 12. In rectangular, though, you usually solve for y. So this is actually a line. You can picture what it'd look like. If you were to go graph that in polar, you'll see the line y equals 4/3 x plus 4. Yes, I was right, right? All right, so we're done. Done. That was a